Hi, everybody. I'm Artem Kaznatcheev, and I'm very excited for this workshop on what makes a good theory from the interdisciplinary perspective. I'm very grateful to the organizers for inviting me to say what I think makes a good theory from my perspective as someone who works at the intersection of mathematical biology and theoretical computer science. Now, given my rather mathy background, I'm going to make my task a little bit easier. Instead of trying to say what makes a good theory generally, I'll talk about what makes a good mathematical theory, just to distinguish it from verbal theories or other kinds of theories that I'm less familiar with. And to sort of spoil you the surprise of waiting for 15 minutes to learn what the answer is community. Community is what makes a good mathematical theory. And this perspective for me is really prompted by sort of the last 2 years of isolation in the pandemic and my interest in evolution, which always pushed me towards a population perspective. And I think the same applies to understanding what makes a good theory. It's not within a given paper or a given book or a given result. Rather, it's within the community that uses those results in that theory to communicate, motivate new questions, etc. So I want to use the next 10 or 15 minutes to sort of spell out what I mean by this with the hope of being able to generate some conversation about this. Now, before I start, I need to make a distinction between modeling and theory, because these are two important concepts. And so right off the bat, I think that everyone is a modeler. Whether you're doing an experiment, doing a field study, reading the literature, just making sense of things around you, you're using some sort of model, usually one that's implicit and in your mind. Now, most of us probably don't then proceed to write down those models. We just use them internally to make sense of the world. And what mathematical models do is they let us share our mental models with others. They formalize these mental models we have and let others who want to address the same kind of problem do it with the tools that we've shared with them. And so these are both very specific to a particular task or a particular problem. What theory does is theory interconnects our models. It shows us when certain models imply certain other models, how certain results relate to certain other results. They motivate us to ask questions that will push towards new models. They help us reason about what makes a model simpler or what assumptions we should make in models, which assumptions we shouldn't. So theory is really the tissue that connects models together, or at least for me, that's what theory is. And what this allows is theory allows us to distribute modeling over the whole community instead of being within a single model or a single modeler. And from this perspective, theorists are connectors. Their primary job is to connect various models for various problems or various experiments to each other. So you might have a field study and an experiment, and you might build a model of one and model of the other, and then theory lets you connect those two to then see how the results relate. So fundamentally, theory kind of lives in the community because it's a way to communicate about our models. And I want to highlight this with an example of two recent papers from the two fields that I work in. So here's a tale of two papers. On the left, we have a recent paper that my colleagues and I published in Mathematical Oncology. And on the right, we have a paper that a colleague and I published in Computational Learning Theory and Theory of Computer Science. The paper on the left came from a multidisciplinary team. We have, theorists, we have cancer biologists, we have a physician, and we connect within this paper. We build models that use evolutionary game theory to think about specifically designed experiments and produce a new methodology for converting certain models into measurement devices that then allow us to use specifically designed experiments to get out these abstract objects, which are called games, as a representation of ecological dynamics in cancer. And I think it's a relatively solid paper. I think it's probably a relatively good model. It's a good experiment. It's well regarded by the field, but it's not good theory. On the other hand, this paper that Prakash Panigadan and I wrote last year is, published in a kind of very average venue, has a pretty standard result, and hasn't made a splash in the field and won't ever make a splash. This is a matter of time. It has one citation now, and then even decades from now, it'll have maybe 10 citations or something. So as a paper, it's not particularly great. As a piece of mathematics, it's not particularly good. But I think it does highlight good theory. And this comes less from the papers themselves or from the results in those papers, rather than how the papers fit into their communities, their respective communities. And we can see this in action by looking at how the community has reacted to these papers, by looking at citations. And so of the United States for this paper, I just picked 4 almost at random. And I took out all the places in 4 papers where our work is mentioned. And these are pretty typical citations. They're almost always saying, oh, other people thinking about game theory and cancer have done work before. That's basically what it says. They don't go into details of the work except in superficial ways, where they might name, the kinds of experimental system that we use. Like they say here, lectin-sensitive and lectin-resistant non-small cell lung cancer. Or they might mention something related to what we did. So something like calling into question the validity of the intertumor competition assumption, which is not something that we call into question directly, but it is related to some of the things that we call into question. But at no point do these citations look at the exact object that we measured. We report some data that's not engaged with. We report some models that's not engaged with. We have produced a new kind of experimental technique that's not used. And the only times you see this, the methods developed here, used or extended, is in follow-up work where one of the original authors appears again, right? So I've done follow-up work since that they use the method, and Jake, Andre, and David have also done follow-up work. But all the vast majority of the citations are kind of like this, and you can pause and read these references if you want. I'm sure you've seen similar citations to your own work before. On the other hand, for the computational learning theory result that Prakash and I produced, the only citation we have engages very deeply with the work, right? It looks at a particular object that we defined. It states exactly the results that we have with that object. And then it then says, here we provide a simpler proof of a stronger lower bound. So they directly improve the results. And then they, in the argument for the improvement of the result, they directly mention, look at figure 1 of this prior work. Right? And to highlight further how much the computational learning theory field is sort of self-aware and cumulative, They can also notice when we've made mistakes in our work. Like, for example, since both Prakash and I were kind of outsiders of the field, there was some prior results that we weren't aware of, and the citing work could then call us out on it and say, these authors were apparently unaware of prior results learning opus automata by Baimel et al. And others. So it's a very different kind of engagement. And I'm sure you've seen these different ways that people engage with work in both how you write your papers or on how your papers are cited. And I think we can use this distinction that I'm highlighting here to identify fields where theory will flourish and where theories won't. And what we have to do is just look for cumulative fields. That's where field theory can flourish, and we can build strong connections between models or between results. And for that, we need to look for direct engagement with prior work. We need to look for fields where new work extends directly prior work, so it takes an existing model and simplifies it or abstracts it, or tweaks it in some way that challenges prior work constructively on its own terms, and that has reviews that synthesize and unify prior work instead of just listing the results. And the question that I have is, if we want to identify fields that have these features from fields that don't yet have these features, can we notice this empirically? And I think we can by looking at citations. In particular, not all citations are the same. And there's already algorithms like this one by Valenzi and Ha and Edzioni, which is used for the Semantic Scholar website, which tries to use the text of the paper to identify if a given reference is incidental, i.e. just mentioning related work, or some comparison to prior work, versus an important citation, one that uses the work or extends the work. And similarly, you can go into further distinctions, as Erickson and Erlandson do, on the motivations that one has for referencing prior work. And some of that motivation falls into things that extend the argument or the data that your work is building on, and others fall into less theory specific, but more social aspects of the field. So, from good aspects like giving credit to prior work to more self-serving aspects like self-promotion, etc., or just defending your self-image. And I think we can look at fields by comparing the number of incidental to important citations they have, or the number of sort of argumentative and data focused citations from the sort of alignment focused citations. And I think this can be done potentially automatically to sort of identify in which fields theory has a better grounding or might fare better. And we can visualize this by looking at citations, by looking at papers and drawing edges between papers that cite each other only if those citations are important. And so in mathematical oncology, I think it'll often look like this, where there'll be papers that reference each other, but almost never in a way that's building on prior work, just mentioning prior work. Or occasionally there might be some papers that are influential, whose method or results are extended, but there's usually not chains of cumulative work. And I think this highlights that the field is not quite ready, or doesn't have well-developed theory yet. On the other hand, in computational learning theory, for example, we start to see much more cumulative chains of work building on prior work that itself built on prior work, that itself built on prior work, that built on prior work. And I think that highlights, to me, what a good theory looks like. If the field is seeing a lot of this building on prior work, then that's a sign of good theory. And if the community is not doing this, then maybe that's not good theory. Or maybe there's still room for improvement. But I'm not sure if this is causing it, or if this is just an observation about the consequence of good or bad theory. But I would definitely want to engage with this population perspective on theory more. Thank you.